I am Devasena. In this lecture, we are going to discuss about differentiator using operational amplifier. This topic is present in the subject linear integrator circuits. Differentiator. The circuit which produces the differentiation of the input voltage at its output is called differentiator. The differentiator circuit which does not use any active device is called passive differentiator, while the differentiator using an active device like op amp is called an active differentiator. Ideal active op amp differentiator. The active differentiator circuit can be obtained by exchanging the positions of resistance R and capacitance C in the basic active integrator circuit. The op amp differentiator circuit is shown in figure A. The ideal differentiator using op amp is shown below. Here is a representation. In this ideal differentiator, the input signal V suffix in is applied to the differentiator circuit through the capacitor C1. The input is supplied to the inverting input terminal of the op amp. Between the input and the output, a resistor R suffix F is connected. This is acting as a feedback resistor. This is indicated in the diagram. In this ideal differentiator, the node B is grounded. The node A is also at the ground potential. Hence, V suffix A, that is the voltage at the node A, is equal to 0. As input current of the op amp is 0, the entire current I1 flows through the resistance R suffix F, that is the feedback resistance. This is indicated in this diagram. From the input side, we can write I1 is equal to C1 differentiation of Vin minus Va divided by dt. That is equal to C1 differentiation of Vin by dt, because the value of V suffix A is equal to 0. Consider this as equation 1. From the output side, we can write I1 is equal to V suffix A minus V0 divided by Rf. The value of V suffix A is equal to 0. So we get I1 is equal to minus V0 divided by Rf. Consider this is equation 2. Now equating the equations 1 and 2, we get C1 differentiation of Vin by dt is equal to minus V0 by Rf. Consider this as equation 3. That is V0 is equal to minus C1 Rf differentiation of Vin by dt. Consider this as equation 4. The equation shows that the output C1 Rf times the differentiation of the input, and product C1 Rf is called time constant of the differentiator. The negative sign indicates that there is a phase shift of 180 degree between input and output. The main advantage of such a differentiator is the small time constant required for differentiation. By Miller's theorem, the effective resistance between input node A and ground resistance becomes Rf divided by 1 plus A suffix V is approximately equal to Rf by A suffix V, where A suffix V is the gain of the op amp, which is very large. Hence, effective R suffix F becomes very small, and hence the condition R suffix F C1 is very less than T gets satisfied at all the frequencies. Differentiator using bias compensation. In practice, a resistance R suffix compensation is equal to R suffix F is connected to the non-inverting terminal to provide the bias compensation. Here is a representation of the differentiator using bias compensation in figure B. Here in the non-inverting terminal of the operational amplifier, the compensating resistor op amp, which is equal to the value of R suffix F, is connected. This is indicated here. Input and output waveforms of the differentiator circuit. Let us study the output waveforms for various input signals. For simplicity of understanding, assume that the values of R suffix F and C1 are selected to have the time constant as unity. Step input is applied. Let the input waveform is of step type with the magnitude of capital A units. Mathematically, it can be expressed as Vin of t is equal to capital A for t is greater than or equal to 0. Consider this is equation 5. Now, mathematically, the output of the differentiator must be V naught of t, that is equal to minus differentiation of Vin by dt, that is equal to minus differentiation of A by dt. If we differentiate the constant, we get the value as 0. So, minus dA by dt is equal to 0. Consider this is equation 6. This is because the magnitude A is a constant. Due to this finite time, the differentiator output is not 0, but appears in the form of a spike at t is equal to 0. As the circuit acts as an inverting differentiator, the negative going spike or impulse appears at t is equal to 0, and after that the output remains 0. Here is a representation of step input applied to the differentiator with the help of a waveform. The step input of magnitude A is applied to the differentiator. Due to this, the output obtained from the differentiator is a spike. This is indicated here. Square wave input signal. The square wave is made up steps, that is step of A volts from t is equal to 0 to t is equal to capital T by 2, while a step of minus A volts from t is equal to capital T by 2 to capital T and so on. Mathematically, it can be expressed as Vin of t is equal to capital A for 0 less than t less than capital T by 2, and it is equal to minus A for t by 2 less than t less than t. Consider this as equation 7. The differentiator behaves similar to its behavior to step input. For positive going input, the output shows negative going impulse, and for negative going input, the output shows positive going impulse. Hence, the total output for the square wave input is in the form of train of impulses or spikes. Here is a representation of square wave input signal applied to the differentiator and its corresponding output waveform. This is the square wave input that is applied to the differentiator. Due to this square wave input, the output obtained from the differentiator is the train of pulses that is indicated in the diagram. Let's discuss the input as sine wave. Let the input waveform be purely sinusoidal with a frequency of omega radians per second. Mathematically, it can be expressed as Vn of t is equal to V suffix m sine omega t. Consider this is equation 8, where V suffix m is the amplitude of the sine wave and t is the period of waveform. Let us find the expression for the output. Mathematically, it can be expressed as V naught of t is equal to minus differentiation of V naught of t by dt. For r suffix f C1 is equal to 1, the output V naught of t is equal to minus dV suffix m sine omega t by dt. Therefore, V naught of t is equal to minus V suffix m omega cos omega t, because the differentiation of sine omega t is omega cos omega t. Consider this as equation 9. So, at t is equal to 0, the output V naught of t is equal to minus V suffix m omega, because cos 0 value is 1. And at t is equal to capital T by 4, omega naught of t is equal to 0. And at t is equal to capital T by 2, omega naught of t is equal to plus V suffix m omega, and so on. Thus the output of the differentiator is a cosine waveform for a sine wave input. Here is a representation, sine input signal that is applied to the differentiator. The corresponding cosine output obtained from the differentiator is indicated here. So far we have discussed about the ideal differentiator. Let us discuss the disadvantages of an ideal differentiator. The gain of the differentiator increases as frequency increases. Thus, at some high frequency, the differentiator may become unstable and break into oscillations. There is possibility that op-amp may go into saturation. Also, the input impedance decreases as frequency increases. This makes the circuit very much sensitive to the noise. Thus, when such noise gets amplified due to high gain at the high frequency, noise may completely override the differentiated output. Practical differentiator circuit. The noise and stability at high frequency can be corrected in the practical differentiator circuit using resistance R1 in series with capacitance C1 and the capacitor CF in parallel with resistance R suffix F. This is indicated in this diagram. In this diagram, in the input side, we have included a resistance R1 in series with the capacitor C1. Similarly, in the feedback path, we have included a capacitance C suffix F in parallel with the resistor R suffix F. This is indicated in this practical differentiator. Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video means kindly share this video to your friends. Thank you.